Okay, here's our lesson on logarithmic equations. Our first goal is to exponentiate logarithms in order to solve them. And we're going to take the log of both sides. We're going to equate bases, like we do in example 1 here. And we're going to equate logarithms. Okay? One thing I wanted to talk about real quick is that when we exponentiate logarithms, we focus on this word exponentiating. And we talked about it in class. It means to make something an exponent. Okay? And so just kind of try to keep that in your mind when we get to those problems. Okay? Okay, so in our first example here, we have two exponential expressions on either side of the equal sign here. And what we need to look at is how can we create similar bases in these exponential expressions so that we can use some logic to look only at the exponents. Because if we have same bases, well, then we will have two equal things that we can only look at our exponents, and then the exponents must be equal also. So when I'm looking at this, I'm saying, well, how could 4 and 8 relate to each other in terms of a base? Or better yet, what base could be turned into both 4 and 8? Well, in my mind, I see 2 as being a possibility. So I can rewrite each of these to be 2 squared to the 3x equal to 2 cubed to the x plus 1. And then what we can do is we can say, well, 2 to the 2 all raised to the 3x, we multiply exponents. And then we could say, well, do the same here. We get 2 to the 3x plus 3. Now what we have are two bases that are the same on either sides of the equal sign. And logic tells us that this entire left side is going to be equal to this entire right side. So that means that our exponents must also be equal to each other. So now we can just ignore the bases and create a separate equation of 6x equals 3x plus 3. Then we subtract 3x, we get 3x equals 3, so x equals 1. Okay, in this equation we want to do what's called taking the logarithm of each side. And so what that means is, in algebra we can often do something to an equation as long as we do it to both sides of the equation. We're just manipulating the equation to our own benefit. And if we, there have been times when we've multiplied both sides of the equation by a special 1, sort of like a 1 over 1 plus 2i, whenever that suits us. Or maybe a 1 minus 2i over 1 plus 2i, the conjugate. Well, this is the same sort of attitude. So I'm going to take the equation, 2x equals 7, and I'm just going to take the log of both sides. All I did was write log next to my two things, and I created two logarithms. Because if the log of 2 to the x equals the log of 7, then 2 to the x must also equal 7. Okay? Then I know that by my power property, this exponent has to come down in front. So I rewrite that as x log of 2 equals log of 7. Now I've got x on the same playing field as my logarithms, and I can divide both sides by log of 2 to get rid of anything attached to x. And then I know that x equals log of 7 over log of 2. And then I go ahead and enter that into my calculator, and I get roughly 2.81 is equal to x. In this case, we're going to do the exact same thing, except I need to see that this nugget right here, this is my exponential nugget. and it's what I will take the logarithm of. So I have to get rid of everything else that's not involved in my little exponential nugget. So I'm going to subtract 4 from both sides, leaving just 10 to the 2x minus 3 equal to 17. And then now what we can do is take the logarithm of both sides. So we'll pull this over here, and we'll say log of 10 to the 2x minus 3 equals log of 17. Now there's two ways to handle this. So I'll handle it the same way we did in class first, and then I'll show you the second way. The first way is bring your exponent down in front, just the way we did in the last problem. 2x minus 3 log of 10 equals log of 17. So we have this in front, and we can divide away our logarithm. Divide away log 10. And you end up with 2x minus 3 equals 1.23. And I'm being approximate right now, I'm kind of rounding. Okay? So then 2x equals 4.23, and then x equals 2.115. Alright? So that's how we handled it in class. One thing we could also do is come back to our logarithm here and say, well, right now I've got this log of 10. And what is our base when there is no base written? What do we assume it is? Well, we assume it's base 10. And when these two match, we can just drop away the whole logarithm. And we get to say that this whole left side is just 2x minus 3 equals log of 17. Which, if you enter this into your calculator, you'll see that it is also 1.23. And so we end up at the same exact answer, but with a couple less steps. If you notice that your logarithm's base matches the base you originally had. Okay, here we have two logarithms on either side of the equation. So at this point you could kind of consider this the reverse of what we just did. Okay, when we take the logarithm of both sides in the problems before, we had to make sure we kept the bases the same, otherwise the equation wouldn't be an equal equation. Well, look at here, we've got two logarithms, both base 3. There's nothing added or subtracted to either side, they're just two logarithms set equal to each other. So I could say, let's say for instance the answer to the left side is 2. Well, that means the answer to the right side must be 2 as well. That's what the equal sign is telling me. One logarithm is the same as the other, which means this part of our logarithm must equal that part. So I can ignore my logarithm and just write this bad boy right here. 5x minus 1 equals x plus 7, and I can solve for x now. So I subtract x, and then I'm going to add 1, and I get 4x equals 8. Divide by 4, and x equals 2. Okay? But this only works if your logarithms are alone and the base matches. Logarithm, logarithm, base match, base match. So then your values match as well. Okay? Okay. Here we're going to talk about exponentiating each side of the equation. We talked about this in class where I said, imagine enumerating something. If you enumerate something, you make something numbered. Well, if you exponentiate something, you make something an exponent. So we're going to create a new equation where each side of the original equation is an exponent. Again, this is where we're manipulating the equation. And for equations, it really doesn't matter what you do to them. as long as, one, it benefits what you need in order to solve for x, and you do the same thing you do to one side as you do to the other. So I'm going to make each of these an exponent. The question is, what base should I use? Well, I want to use a base that benefits me. And a base that matches the base of whatever logarithm you have will undo the logarithm by inverse properties of a logarithm. If a logarithm's ever an exponent above a base that matches it, like base 5 here, then we can eliminate the whole logarithm and leave just the value behind. So then we have to do the exact same thing. Our 2 on the right side becomes the exponent above 5, our base that we chose. So again, these bases match here and here, so we can eliminate this, leaving just 3x plus 1 equal to 25. So then 3x equals 24, and x equals 3. We subtracted 1, we divided by 3 here. So there's our solution. Okay? Okay, so in this problem here, we're going to have a solution, we're going to have two solutions, and they're going to be extraneous. And extraneous basically means we don't know for certain, if they work. Okay? And so we'll have to check. Basically, you're just going to test both solutions in the end. Okay, so we need to condense these two logarithms and say, well, log of 5x times x minus 1. Again, that's because two logarithms were added together, and now we need to multiply those two. Alright, so we have log of 5x squared minus 5x equals 2. So we're going to exponentiate these, and since we have no base written, we assume base 10. So I'm going to say, well, that's 10 log 5x squared minus 5x equals 10 squared. So this whole part goes away, just like in the problem before, and I get 5x squared minus 5x equals 100. Now here is where we get a little tricky. We need to bring the 100 over by subtracting 100 and making our equation set equal to 0. So 5x squared minus 5x equals, minus 100 equals 0. Well, all of these have a greatest common factor of 5, so I can divide everything by 5. And divide by 5, and this becomes, I'm going to pull this up here, this becomes x squared minus x minus 20 equal to 0. Okay? Alright, so now you've got a quadratic in standard form, and we need to solve. Well, the first time we solve, we always try to factor first. This guy factors to x minus 5 and x plus 4, which equals 0. Set each factor equal to 0, you get x equals 5. Set the other factor equal to 0, and x equals negative 4. Now we just need to check to make sure our solutions work. So I'm going to plot here, and our original equation was log 5x plus log x minus 1 equals 2. Okay? And our possible answers are negative 5 and 4. What was it? Excuse me. Positive 5 and negative 4. Sorry. So positive 5 and negative 4 we're going to check. So first let's check 5. Log of 5 times 5 plus log of 5 minus 1. Does that equal 2? So I enter that in my calculator. I get log of 25 plus log of 4. Yep, my calculator says that's 2, and 2 equals 2. So I checked it, and I'm good to go. Alright? Then we go and say, alright, let's look at negative 4. So we get log of 5 times negative 4 plus log of negative 4 minus 1. Does that equal 2? And you enter that in your calculator. So I'm going to enter in log of negative 20. And what we end up seeing here is that when you enter these in your calculator, you get a non-real answer on this guy, which makes sense. What this essentially says, if I multiply the first one out, is log base 10 of negative 20. So the question is, 10 to what exponent would ever equal negative 20? There is no exponent that will ever change the sign of a base, ever. I could plug in the largest positive exponent ever, it would just be a really big number. If I plug in a really negative number, like negative 1,000, let's say, that doesn't change the sign. It just makes the 10 now a really small number. And if I plug in 0, 10 to the 0 is 1. So there's no number that we can plug in that would ever turn 10 into negative 20. Same for log of negative 5. Nothing's ever going to make it be negative 5. So 4 is not an answer. 5 becomes our only real solution. And lastly, here we have some example problems for you to practice with. These are great ones to bring in. Give these a try. Come see me, and we can work on these together. I want to talk through these error analysis real quick, and we'll go from there. All right. So here we have 4 to the x plus 1 equals 8 to the x. So they take the logarithm of both sides. And when they do that, the exponent gets to come on down. And so we eliminate the bases here. And notice they wisely chose log base 4 because this was base 4. And so this whole part goes away, leaving you just x plus 1. So then the only question is where to go from here. Well, they said, well, this must be 2 because 8 divided by 4 is 2. Well, that's totally wrong, okay? What the question you need to ask yourself is, 4 to what exponent equals 8? It's certainly not 2. 4 squared would have been 16, okay? So then what I would do is I would have used change of bases here. I would have said log of 8 over log of 4, and that equals 1.5. So we should have had x plus 1 equals 1.5x, and then we can subtract x from both sides and get 1 equals 1/2 x, or x equals 2. Okay? In this other problem, where we are describing the error, the problem is that they exponentiated both sides to the wrong base. They chose the natural base, but our base in our logarithm was 2. They should have used a base 2. That's the only way the inverse property works. So you can't get at a value like this by exponentiating to a base that doesn't match the base of your logarithm. So if I'm doing this problem, I raise both sides above 2. So I have 2 log 2 of 5x equals 2 to the 8. Okay, so then I get 5x equals 2 to the 8. 2 to the 8 equals 256, so 5x would equal 256. So then x equals 256 over 5, which is 51.2. Alright, hope that helps. Like I said, try some of these, try your homework, and come in with questions. If you would like an appointment, please email me, let me know, and we'll set one up. Alright, thanks.